Yep. Right. That was one other thing to say, which is that I know I have forgotten to upload videos from last week. Maybe others. I'll dig in the folder and make sure everything goes up. Right. So this week's stuff, there is more, is actually finally going into solid state, if you like. What we're going to look at is, instead of a molecule, let's have a look at a crystal. We'll define a crystal a little bit more precisely in a later week, but essentially a crystal for our purposes is going to be something that repeats regularly. So you have some motif and then it repeats after a certain distance. And what we'll actually be doing this week, that kind of acts as a bit of a revision exercise as well, is essentially doing what we did last week for a pair of atoms, but doing it for an infinite chain of atoms, or at least a rather large chain of atoms. Fortunately, this requires one little mathematical trick, but apart from that, it doesn't require much new information. Right, let's see if I can find which button does what. Does that... No, not that one. Does that one get up my whiteboard? No, that gives a horrible close-up of me. Right. So what we had, I had the right way up. Sorry about my manicure, etc. Last week we had two atoms. And on each atom we had a basis function, and we converted the Schrödinger equation to a matrix equation where we had our matrix, not really on the board. Let's come down a little bit. So we had H, I, H, J, 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 I, C, I, C, J, C, C, J. And then we've got some energy for a given wave function. We converted a differential equation, a Schrödinger equation, a matrix equation, in terms of how many of our different types of basis functions we would use to build it. And what we ended up with was a sort of a picture in energy, where we started out with our energy levels of the atoms, and when they interacted, we ended up with a new energy level where, like the particle in the box picture, because we had the electron could be either on atom I or atom J, we effectively given it a larger box to move around in. And when we punched through the maths, we followed our recipe for quantum mechanics. We found that there was a more stable energy level. And so before it was interacting, we had the electron energy was epsilon I plus epsilon j, the energies of the electrons in the atomic states on the atoms. But if we had one electron in each atom, we could put them both into the more stable state once we form the molecule, and we would stabilize the molecule, which is our quantum mechanical picture of binding in a molecule. So this is a molecule. Now, what we'll be doing this week is shifting to crystal. And essentially everything we had before is going to stay the same. I'll learn these keys. Right, I'll go back to the screen in a second. But what we're going to do is, instead of having atom I and atom J, we're going to have a big long chain of atoms. So instead of atom, we're going to label them with different indices, and so we've got I'll have to check how consistent I am in my labeling. Atom 1, 2, 3. They've all got basis function on them, and they're all going to be a distance A apart. Yeah, so I've got one and but anyway, they're all distance A apart, and we're just going to work in one dimension. So it's going to be a one-dimensional chain of atoms. Does that make sense as a picture? So we've just got this big long thing that just goes on as far as you can think, and then one more effectively. Right, but what we're actually going to do is it's a mathematical trick. Instead of this thing going on to infinity, is a little bit tedious on computers and conceptually. What we're going to do is we're going to say there'll be very little difference if we were to kind of curve our x-axis. I've drawn this with, I don't know, 8 or 9 atoms. I'm not really going to curve it, but what I'm going to do is to have the last atom connected back to the first atom. If you like, it's a ring of atoms, and there's going to be n atoms in the ring. If I've got my notation consistent, there will be, I'll write this as n minus 1, n minus, so that there'll be atom 0, 1, 2, 3, n minus 1, so n atoms in the crystal, and then it goes back to where it started. So I've drawn it as a ring, this sort of curved x-axis that joins up on itself, but really it's just going to be one axis that goes forever. It's just, I've got this weird geometry where the first and last ones are connected to each other. So somehow keep that sort of, it's just a straight x-axis, but it does join back to itself at some point. You can think of it maybe, and this is what we'll see, if you think about a sine function that just repeats. So if you like, this point and that point are sort of close to each other, even though you can pick which image of the repeating thing together. Okay, a little bit more notation. So I think I'm just saying what I said. We've got a 1D chain of n identical atoms. Each atom has got an atomic orbital on it, so one of these atomic states that we had from last week. So everything's the same as last week, but it's going to have more of these atoms. And the atoms, they're all going to be equally spaced apart, and we're going to call this, I'll refer to it later on as a lattice constant. The lattice constant is the repeating unit. So if you think there's an atom every A, that means every A I've got the same thing going on again and again and again. So it's the unit of repetition. It's just a bit of language. And we're going to do the same things we did last week. This expression orthonormal. What it means I've got an atomic orbital I on atom I, and an atomic orbital on another atom, all the same one. If I do this integral over the pair of the functions, I get 1 if they're on the same atom, I get 0 if they're on different atoms. We had this last week we used it in our sort of simplification of the Schrödinger equation to get this. But what we're saying is that essentially the functions are pretty well localized on their atom, and there's not really much overlap with when you do the integral by multiplying them together. It's more or less 0 if they're far apart. A more detailed model would allow them to overlap if they're on next nearest neighbours or whatever, but that's for us. Okay. Now we go through our recipe. So if you remember, the first thing I said you do is you write down the classical Hamiltonian for the system. So what we're assuming for now, and we'll put in a bit more stuff later on, but we're assuming that the nuclei, the atomic centers are really heavy compared to the electrons, so we're just going to put them in those locations. So we said 0, A, 2A, 3A along the axis. We're going to keep them fixed, and we're just focusing on the Hamiltonian for the electron. So what I've written it as the Hamiltonian for an electron is the kinetic energy of the electron. So the same thing as we've had before, p squared upon 2m for the electron whizzing around. And then what I've got here, this summation, it means this electron interacts with each of the nuclei in the crystal. So I've got electron with charge E, the nuclei are going to have some charge. We're going to do sort of hydrogen, so we're going to assume they've just got a positive charge on them for now, but just multiply that by the atomic charge. Bigger by nuclear charge. So my Hamiltonian with the kinetic energy plus the potential energy, Coulomb interaction of the electron with each of the positively charged nuclei. So the kinetic energy is the one we've seen before. We're not actually going to need this differential operator, but that's what it is. It's this square of the momentum operator. So we write down the classical operator, put in this differential operator, but then we're converting to this matrix notation. Second. And so these interaction potentials are given by this expression. So it's the square of the charge. So again, I'm specializing to the fact that the electron has got charge of an electron, and the nucleus essentially is a proton in this case. So it's a fixed thing with a charge of plus the charge on an electron. So I've got E squared on the top, where E is the charge on an electron, and then 4 pi epsilon 0, and then at the bottom, we're just in one dimension, so it's a distance of so x is the position here of the electron, and J a position of the Jth atom. So that one goes there, yeah. I'll put it back in a second, but just to be clear that sort of x is the position of the electron. That's the electrons flinging around, and then it's talking to the Jth nuclei. So that distance there is x minus IA. And then our sort of matrix formulation, we need to sandwich our Hamiltonian operator between pairs of basis functions and do this integration, what we did last week. So that came from making this approximation that the real wave function will be a linear combination C0 of basis function 0, C1 of basis function 1. We put this linear combination, we plugged it through, and we differentiated it to get the best. What we found was a matrix equation with these matrix elements given by these things. And we're going to use the same trick or the same observation as last week, that if our Hamiltonian is a Hamiltonian for an atom, but we just contain the kinetic energy and the interaction with a single atom of the so if I've got T plus the interaction with J, and it interacts with the atomic state on atom J, then that is a correct Schrodinger equation. Get the energy that on that atom and what we're going to do is to break down this Hamiltonian to, depending on the indices, depending on where we're looking at the we'll be able to look at the potential interaction with the nucleus that's close across and the rest. A bit like we did for the molecule, where we had a case where we were looking at the electron on its own atom and talking to the other nuclei. So, form that's writing out to make equation in slightly longer form, HC equals BC. Okay. Get these matrix elements by doing this. Now, it's going to be this situation. What we're going to do is we're going to take this Hamiltonian, so we work out the matrix element Hij by sandwiching our Hamiltonian between the I and J. Once and we integrate over all space with 0 up until the end of the chain. Now we do what I kind of said. We rewrite our Hamiltonian as kinetic energy plus the potential energy of one of the J, That's the one that corresponds to the basis function got on the right. We're going to pick out one of the potentials, one of the potential energy interactions with J, one that matches this right-hand index here. Then on the rest, we've got the rest of the Hamiltonian is the interaction with all the nuclei which aren't the one we picked out there. So we've got our total Hamiltonian with sum over all the talking to all the nuclei, and we've just rewritten it with this one particular one picked out here, all the others over there. I could have all of this inside. Now I'll go to this script. There was a script that we did last week. Is T plus Vj on phi j. This gives us epsilon j. Gives us the energy of electron on that atom. If we go back one slide, it's that equation here. So we're using our knowledge of the solution to the atomic problem. Let's write that out. So we've got, if we've got the kinetic energy plus the interaction with nucleus J, so this is our Schrödinger equation, the kinetic energy plus the potential energy of just a single atom. And we've previously worked out the solution to the atomic problem. We know it satisfies the Schrödinger equation, so H psi equals E psi is the generic differential version of it. We've solved that for our atom. I wrote that off the top of the board, you can't see it. Yeah. So if we have an integral phi I t plus v j phi j, all those things functions of x, I've got this integral. So if I've got that, then this bit here, different colour, this bit here, we can substitute in there. So this is equal to basis function I, and then epsilon j phi j. So we're assuming we know how to solve the atomic problem. We've already done it. And what we're using is our basis function, our things to set up the problem are those functions that exactly satisfy this condition already. So epsilon j's energy of electron on atom J in vacuum, so just if there's nothing else around, it's a number, so it's the energy of that, so I can rearrange that to, it's actually equal to, I can take that outside the bracket. I'm ignoring the, shouldn't do that, complex conjugate, but it doesn't make any choice. Yeah. So I can take the epsilon outside the integral sign, and that's equal to epsilon j, then this Kronecker delta, this thing that's equal to 1 if I and j are the same, or 0 if they're different. We've agreed beforehand that that will be the case for our basis functions. They're orthonormal. If they're on different atoms, they're far enough apart that when I do this integral, I'm going to get a 0 over just the functions. That's the same trick we did last week. Is it okay if I go back to the slide? So that's what I've done here. This thing here. This is the Hamiltonian just for atom J. These are safe at the end of your atom J, and this quantity delta, whether this thing on the left, same value. And then I've got some integral, sum of integrals of these interactions over 3 centre things. So basis sector function J, the Coulomb potential coming from atom A, and then the third get to the basis function. Yep, I went down on the slides. So that taken off the previous slide. Essentially, this summation here contains 3 types of so if I and J are the same, I and J, my things on either side are the same, that means I'm talking about the basis functions on the same atom. So if I equals J, then I've got integral of phi I squared is VK. So I've got the integral of this phi I, because I is equal to J, so I've got the same thing, so I've just got the square of these functions. And we know quantum mechanically, if you like, that this is the probability for the electron on that atom to be at a position X. So it's this weighted probability of the electron on this atom, sort of in its cloud around the atom, interacting with the kth nuclei. So it's conceptually, you've got the nuclei at K, so we've got a charge of +1 there. Let's see this one. Small there. Yeah. And we've got an electron in wave function I. So the total integral over all this thing, so there's one, the electron is in this state, in that case, and it's the interaction of the electron with the nuclei. Oh, it's fiddly. So if I and J are the same, then the electron is kind of sat on on atom I, and it's interacting with each of the other nuclei. So I'll have an electrostatic interaction with the nearest atom, the next nearest atom, and all the other ones, and it'll drop off as 1 over R as it goes on. If I and J differ by 1, got the same picture as we had last week, which is that the electron can pop from atom I to atom J to the next atom. So the interaction with the other Coulomb, but with the other potential, can allow it to hop to the next state. To the next atom. So that's the thing that lowers this kinetic energy, that stops them being located in an isolated atom. And if they're further apart than 1 next nearest site, then I'll get 0. Probably not helpful, but you could write this down in this form here. So I've got, if I and J are the same, means I've got HII, or J2. I've got something on the main diagonal. I've got this atomic energy plus V0, the interaction of the electron on atom I with all the atom nuclei. Then I've got minus theta popping to the next electron, because when the indices are different by 1. Probably more useful to actually just write out the matrix. So if we're on the diagonal, we've got the epsilon, the atomic energy, plus V0, interaction of an electron on atom I, but feeling an attractive interaction from all the other nuclei same. That's sort of weighted by the distance, but we're summing up all those interactions, bundling up into V0, adding it on to the atomic energy. So that's going to bring down the energy of all.
Yep, and why the ones just off or T, but why the ones off right and bottom left?
Yeah, this is the trick. So the ring joined up, so this means that n minus 1 is the next nearest neighbour to 0. So put this one here, this one there, because the ring joins up the next nearest neighbour. Now strong, something logically a bit weird going on. Okay. The reason we do it, we have a long chat with group theorists or something like that. That this matrix with the T on those two corners quite different one without the T corners. Actually, it's very similar, but there's some tricks you can use if those T's are there that don't work. So that's what it's going to look like. It is a bit fiddly, but essentially it was this solid state basic. It's called 1D crystal, or light binding model of a 1D crystal. Look it up for you in a minute. So if you look at this top bit, this 2x2 top corner, that was what we had for our molecule. But now it also talks through the rest. And this means that, if you like, the electrons are no longer confined to one or two atoms, but they spread out over the whole of the crystal. And this is the basis, again, of our sort of fact that we'll get some states of much lower energy because they're states where the electron move over the whole crystal. Lower its kinetic energy, it's got more space to it. Right. What possibly we'll do on Wednesday is to actually do some of this numerically. I've sort of got an example here. So if you see what I've got here, if I pick a particular number of atoms in my crystal, let's say I have 50 atoms in the crystal, I can write out this Hamiltonian matrix. I know what all the things are. My hopping integral is parameter in my model. I can estimate it from atomic properties maybe. So I give it some value. My atomic energy, I've got something I could measure, maybe using spectroscopy in the lab, so I can shine light and see what energy I needed to extract. And this V0 I can make it through non-interaction with the other nuclei. I could come up with some model. So I can come up with some parameters to put into the model that are reasonable. I can set up this matrix, Python, or C++, or MATLAB, or Maple, or Scratch, or whatever else you use. I'm not sure there is an eigensolver in Scratch. We can see, there quite possibly is. And what we want to solve is our quantum mechanics says that the final thing we'll solve is HC equals EC. So I'll have our Hamiltonian matrix and its eigenvalues, this is an eigenvalue equation, are the energy levels of the system, and the vectors C, the eigenvectors, tell us how much of each of the different basis functions we need to use to build our eigenstates, to build these states of the electrons in the crystal. So what I'll do is I'll go through numerically, answer any questions, take a little break, and then we'll go through and see if we can get the same results that I get numerically, but analytically using a couple of tricks. So what I've done here, I've got all the code and fire up. So let's just do it complicated. Build a big matrix. We're okay with this term, diagonalize it, find the eigenvalues and eigenvectors. I'm finding the eigenvalues and eigenvectors of this matrix H that we've just spent a long time defining. I'm going to feed in some parameters. I'm going to say epsilon, this energy of the electron on the atom before they were brought into a chain and interacted. I'm going to call it -7 electron volts. So a hydrogen atom, it's 13.5 or something like that. So it's something that's representative of the least bound electrons in an atom. It's just representative. I'm going to say my interaction V0 with all the other nuclei. So if the atom sat on one of the nuclei, but it sees cores of all the others, it gives it -0.5. It's a stabilisation from the attractive interaction with all the other cores gives it a minus 0.5, and I'm going to have this hopping interval as minus 3, which means it's quite a big chance we are hopping one atom to another. So those are my parameters. They're all energies, they're all in electron volts here, working SI units. Wanted to have 10 to minus 19s flying around, but they're working electron. And what I did was to set up an array, a NumPy array, and so essentially I had a loop, and for each row, apart from the top and bottom one, I said that on the diagonal element, so on the indices of the arrays, but where they're the same, I had a loop for I equals 0 up to n-1. Diagonal element, qualifier up to so on the diagonal element, that epsilon plus v0, and either side of that I put minus 3, and on the top row and the bottom row I did the same, but remembering that the thing that's to the right of this one actually to back to when they loop around. Then Python, MATLAB, whatever, have built-in eigenvalues, vector solvers. So for small systems, remember you can write out this determinant and solve the characteristic equation and extract the eigenvalues. This is a bit tedious for say a 50 by 50 matrix, writing out a polynomial of order 50 and finding the roots of it. So I'm just going to use the computer. And what I get out of that 50 by 50 problem is 50 eigenvalues, and I've sorted them by energy. So they go from minus, I guess it's 13.5 up to 2, like 2, no, it's minus 1.5. If you want to count them, you could find the corresponding to those 50 states that I put into the model. That means I've got 50 states come out. We're not working with where we're getting that spin on the electron, so each of these states have 2 electrons, so in total I could put 100 times 2, so I could put 50 times, I could put 100 electrons. But if there was 1 electron in that, then I could have a hydrogen, then I would be filling it up to halfway. That numerical thing, I'm just trying to look at what solutions look like. If you remember, that the epsilon, so the energy of the electron on the individual atom, minus 7. Then I've set up this. Should reprogram this bit. So minus 7 was the energy of all the electrons on the isolated atoms. But now once I've brought them together, a whole bunch of states that have energies that are smaller than that 7. I put electrons into those states. They're in a lower energy state. I've released energy. I've made a happy crystal. If I had to then keep putting extra electrons in, they would conversely be going into higher energy states, and I'd be losing out my binding. So So I've got the right number of electrons. So if I've got the right type of atom, only sort of 1 electron per atom and gaining energy, and the other one that's just going to trade off, but fully filled up and get the right gain. So those are the eigen values, the energies. Each one's a valid solution to the Schrödinger equation in our approximation, where it's this linear combination of atomic orbitals, and each of them can accept 2 electrons into it. Now, what do those states actually look like? A couple more things I've spotted. Apart from the first and last states, there are 2 states of exactly the same energy. Something that will be of interest later on, the density states, how many states there are in a given energy range varies. More of them will fit some less. Or this function, broad scale, is like something like the standard functional. And the other thing is that the energy difference beginning at the top is 4 times our bottom. So all these things kind of suggest there might be a nice analytical solution to this, which we'll try and find. Second, last thing I just want to say before taking a break is, so that was the eigenvalues. The eigenvectors, what I get are the values which, for a given eigenvalue, I get a vector, an eigenvector for it, which gives me a value of C0, a value of C1, how much each of the atomic functions contribute to that eigenstate. And what I've drawn up here is I've plotted out the values for different. So these are how much of the basis functions are. And I think essentially you can, if you look at the, very unclear, but there's a sort of amber one here that goes from 0 up, down, up, and it basically it's a sine function. So what this means, so I've got HC, so I've got H, so this E is my list of eigenvalues, which are electron energies in the crystal, and the C are the eigenvectors. You remember my real wave function, it's approximately going to be equal to Ci phi I. So I'll build it up from a linear combination basic function. So when I solve and get this eigenvector, I know how to build my full wave function. So if it was something like that sine wave one, I would have my real wave function. So I've got 0 at the beginning for that first sine function. So I've got 0 C0. If I do it for just 4, C1 is perhaps at the top of the sine, so it's going to have a 1. So I've got this wave function. I've got sort of plus C1 phi 1. Then C2 is perhaps 0 again if I'm plotting out that sine one, and then I've got a minus 1 for the minus phi 3, and then it repeats if I've only got 4 atoms in my chain. So I get a wave function over the crystal that's a linear combination of my solution to the atomic problem. And the thing is that they're going to be periodic. This is the trick we're going to use in a second to get the analytic solution. essentially because it's periodic, there should be a Fourier series solution to this thing. So we'll be able to write the actual wave functions as sinusoidal amounts of trigonometric function the distance of change. Right, I'm trying to make things clear, but that means I take ages to make through this stuff, so it's swings and roundabouts. But I'll stop at this point. I've tried to show you where this Hamiltonian came from, numerically what it looks like, try to give a little bit of a feeling for what these states and stuff mean, what they the implication. We'll do a little bit more maths and testing to actually extract an analytical version of these results. And then we'll sort of compare it to a couple of bits, and that will be it for today. So I certainly want a bit of a break. I imagine you probably want a bit of a break. What's the time? About 5 to, so about 5 past. I'll start watering again. Thank you. Just